Okay, Assalamualaikum and good morning. Sorry for the delay. I'm having problems with my laptop. So let me just start presenting. Okay, can you see my screen? Okay, good. Right, okay, so today, remember what we are doing? We are still in the canonical ensemble, what we call chapter. Okay, so let me just write that. Oops, not red. Black. Yeah, we are still in canonical ensemble. Okay, and we have seen how to one is able to use the idea of partition function, okay, and we applied it to the spin half system and then the box system, which are essentially in those cases in the box system, for example, you just have translational motion. And then last Monday, we started to do, for the case of a molecule, you consider the case of rotational motion. So today, what we're going to do is to look at the case where, okay, we will look, we will focus specifically for the case of the diatomic molecule and then look at vibrations. Okay, vibrations in for diatomic molecules. So because of the structure, for example, it's not just a simple point particle. I'm having a problem with my tab here. So for example, you have a diatomic molecule, one have possible vibration in this manner, for example. So this sort of vibrates in that way or that way. So you have vibrational modes for the diatomic molecule. Okay. So we need to be able to model this. So and vibrations are really a form of oscillations. Forms of oscillations. Okay. So what one can do is to approximate using what we have seen in the standard oscillation in physics being given by harmonic oscillators. Okay. So what one need usually just to have this approximation, one really need just a potential. So there's an attractive potential between the two atoms of the molecule. Attractive potential between two atoms of the molecule where, let's say, the molecules are separated by distance d, just to give you a physical idea first, and then it started to sort of displace the mean position. For example, over here, the mean position could be here. It starts to oscillate in this way. Maybe I should draw a different diagram. Let's see over here, one could have this kind of motion, and then another kind of motion going out. So in this way, this one is your equilibrium position. So what one does is to, one needs to have some kind of potential that does that, that allows that oscillation thing. So usually what we assume there will be a kind of minima. So there will be a minimum. Okay, and let me just write the potential first. VR, and then this is approximated by an expansion respect to this equilibrium position over here. So this is R minus D dV dr, and then the equilibrium position here is D. So that means one consider this to be your sort of a minima thing. So this will be 0, and then if you continue at least to second order, then you have R minus D squared d2 v dr2, and then evaluate at the equilibrium position. Okay, so in other words, what we have over here is essentially a constant here, and here is the quadratic term. Which is like in the case of the harmonic oscillator potential. Okay, so so that's the rough idea. And when you do, for example, QM of harmonic oscillator, I hope you have done that. Okay, one has these energy levels epsilon n given by h bar omega. Omega will be the natural frequency of the oscillation. Okay, usually can be expressed in some physical thing, and then you have these levels of energy be given by this integer n. Okay, or it doesn't have to be z plus. Let me remove that. You can have it as okay, maybe I just write in terms of the numbers themselves, 0, 1, 2, and so on. Okay, so you notice by from the solutions of harmonic oscillator in quantum mechanics, so once you have these energy levels, you can start again writing down your partition function. So what's the partition function in this particular case? So let me push it out because I'm not having enough space on my tab here. Partition function is given by z equals to the sum over all energy levels. So here can be from n equals 0, like this one, to infinity, of exponent minus h bar omega n plus a half over kBt. Okay, so this is the energy levels used. We normally previously we write it as E minus epsilon I kBt. So now we need to sum this. So let's just give you a flavor of this. What is the sum of the terms looks like? Okay, so this is h bar omega. When n equals 0, you have only a half there. So then you essentially have h bar omega on 2 kBt. And then the next term will be E minus 1 plus a half, that means 3 over 2. So 3 h bar omega on 2 kBt. The next one will be 2, and that gives you minus 5 h bar omega on 2 kBt, and so on and so forth. Okay. So as you can see, from each term goes to the next one, you are just multiplying with exponential h bar omega on kBt. Okay. So in other words, this is really a geometric progression. With r equals to E minus h bar omega on kBt. Okay, so you multiply this to that, then you get that, and this with that, and then you get that, and so on and so forth. And essentially, we know how to sum this what we call geometric progression. In the limit, it's going to be s equals to a1 minus r thing. So let me put this in curly bracket. Yeah, as a side note. So in other words, what's your a here? A is your first term. So your first term is that. So you have e minus h bar omega on 2 kBt divided by 1 minus r, and r is given by that. So that is 1 minus e minus h bar omega on kBt. Okay. So is your partition function for the case of the vibrational motion. So before we move to look at the free energy and so on and so forth, let's look at the two different extremes. Okay, the first extreme is for high temperatures. So this is given by the following. Okay, and this implies that your E minus h bar omega on kBt, or 2 kBt, sorry, 2 kBt can be approximated because t is going to be very large. So this whole term is going to be a small number. So we can essentially express it as a series with the only first order term coming in. So that is h bar omega on 2 kBt. So one can plug this into the answer for the partition function. So you just plug this in here and here. By the way, can you see the cursor? I'm moving this cursor now. Somebody? Anyone? Can you see the cursor? I'm moving my cursor now. Because sometimes it does. Oh, you can't see it. Okay. All right. And then so what we need to do is to take this expression and substitute inside your Z. Z, which is this one. Okay. So, right. So let's do that. So we have Z now being approximated in this way. 1 minus h bar omega on 2 kBT here, divide by 1 minus 1 minus minus h bar omega on 2 kBT. So I'm just going to write that. You can do the algebra yourself. And that will give you, should not approximate that, it should be equals to kBT on h bar omega. Okay, so now it becomes simpler in that sense, so one can look at the physical quantities at high temperatures. So the first thing that one can actually try to do is to write down the free energy, which is minus kBT log Z. Okay, and that is given by minus kBT log of that term there. Okay. So once you have your free energy, one could start writing down some thermodynamical variables like entropy, for example. Again, these are just pretty standard thing that we are doing. Okay, like before, partial F, push this up, partial F, partial T. So one needs to differentiate that. So here again, no, you just need to know how to do the differentiation for each factor. Log kBT on h bar omega. So I'm just differentiating that t here, and then you have another t over here. So we need to do another part, which is plus kBT, and then you take the differentiation of the log, you get 1 over that, which turns out to be this. And then that's differentiating the log, but you need to differentiate the argument inside the log, which is multiplying t here. So that gives you kb over h bar omega. Okay. So you can simplify this, and then you can actually get this to be kb log of kBT on h bar omega plus 1. So you can see that that will be the entropy for at high temperatures. And the next thing that one usually does is to calculate your heat capacity. So again here, I think you can do the differentiation yourself. I'm just going to write down the answer. So essentially the vibrational mode just gives you a contribution of Kb at high temperatures. Okay. Now the other extreme will be the low temperatures, but okay, for the other extreme, use the exact Z expression. let me just write that thing down again. Z equals to E minus H bar omega on kBt divided by 1 minus E minus H bar omega. I think there's a 2 somewhere. Let me go up. Yeah, there's a 2 there. So there should be a 2 there. So probably yeah. Let me check my own calculations here. Yeah, there should be a 2 here. And then again, what one needs to do is, oops. What one needs to do is again work out all the expression. The first one is your free energy. So here again, when you take the log of two factors over here, you in this case a division, then what one does is to take the log of each. The numerator, for example, log of E minus H bar omega on 2 kBt, and then for the denominator you have to put the minus sign because it's 1 over that. So that would be the log of 1 minus E minus H bar omega on 2 kBt. Now one could simplify this further because your log here is the inverse function of your exponential. So one can simplify that. So that gives you you get your minus sign here, and this minus sign you give a plus. So that's kBt times H bar omega on 2 kBt. And then the rest is the same like before, so that will be a plus. Oops, sorry. kBt log of that. Again, I made a mistake here. Now, let me rewrite that again. There's no factor of 2 there, so that's kBt. Okay, and well, I mean, the only thing that you can simplify that is that H bar omega with 2 plus kBt log 1 minus E minus H bar omega on kBt. Right, so one has written, this is actually the exact free energy here. So one needs to do, for the case of entropy, so this is pretty lengthy. Do I want to do everything? Okay, now let's just write down everything so that you can see the working. Entropy is S equals to minus partial F partial T. So the only place where you have T here is here and here. So one can ignore this part. So there for the first factor, you get minus kb log of 1 minus E minus H bar omega on kBt. And then you have to differentiate the log. So that gives you minus kBt coming from here, okay, and then the differentiation of the log gives you 1 over 1 minus E minus H bar omega on kBt. And then you need to differentiate the thing inside the law here. Okay, so that gives you the only term, your 1 is constant, the only term here is that negative exponential, so you have negative exponential here, and then this is also a function, okay, so we need to differentiate this function with respect to t, and that gives you the factor of h bar omega on kBt square. So really there is a minus sign multiplied by minus sign because you differentiate 1 over t. Okay, so that is the whole thing. So I think I'm going to skip some steps to save me from writing everything down. So let me just write the answer here. Minus kb log of 1 minus E minus H bar omega on kBt plus H bar omega on T divided by E H bar omega on kBt minus 1. Now you can see it as you progress further, the more differentiation that you have to do and the more terms will seem to come up. Okay, but let me just, so the next thing that we want to calculate essentially your heat capacity. So remember what is said, heat capacity is T times partial S partial T. So here again, one needs to differentiate this part, okay, inside your log here, and then one needs to differentiate your numerator here, and then one needs to differentiate the denominator. So you can see that it's going to be quite messy, but let me skip all the steps. You try to check for your own self. Please try to do that. Get used to the calculations. After differentiating all of them, you finally find some of the terms cancel off, and then your answer reduced to the following: h bar squared omega squared on kBt squared times E h bar omega on kBt divided by E h bar omega on kBt minus 1 squared. So that's your final answer, which I leave you to as an exercise there. So what actually happens over here is that, okay, at high temperatures, if you look previously at high temperatures, your heat capacity, oops, where is it? Heat capacity, come on, sorry about this. Yeah, your heat capacity is just a constant, your Boltzmann constant. So as temperature goes higher, the heat capacity tends to a constant, but you can see that, okay, in your other parts of your now other regimes of the temperature, you have this complicated function involving your 1 over t squared here, and then your exponential here, exponential square here. But really you can see that, okay, this exponential is going to dominate over the t squared over here as t goes lower. So let me write that thing down, I suppose. As t decreases, so this is going to be large, but because of this, it's going to be larger than 1 over t squared because it has other higher order terms. Okay, so this is going to be dominating over that. But then you also have this at the denominator, which is now square of that. So in other words, effectively, it will be it will decrease as exponential minus 2h bar omega kBt. Okay, so at lower temperatures, no, in the end it will goes to 0. Okay, so there is a picture. I think I better just cut and paste. Is this it? Yeah, vibrational thing. So let me cut and paste there, take a snapshot. So essentially your heat capacity over here will look like this. Okay, so at high temperatures, for example, okay, at high temperatures here is T over, I think this is, can't remember what it is. I think some reference temperature, but never mind. Okay, whatever it is. Let me look at my book because I cannot see, it's not so clear there. It is sorry about this. Okay, there's a theta v which was defined. Okay, this is T over theta v, where theta v is coming from so theta v is defined as h c nu over kb, where nu is your frequency of your vibration. Okay. But whatever it is, no, this at this end, for example, your T becomes higher, and it approaches at here is C on kb. Okay, this is C on kb. So remember that your capacity, heat capacity at higher temperatures is just kb, so it approaches 1 over here. Okay. Approaching 1. In between, particularly at the lower temperatures, you can see that there's as you go the other way, not increasing T, decreasing T, you sort of make that exponential decay there. Okay. But and it goes to 0. Okay. So okay, what else needs to be said? Yeah, there is a table which one can actually try to look. Let me just go back to the book. There's table below that gives you, okay, this characteristic temperature, for various what you call various diatomic molecule there. Okay. So one could essentially look at this model using the harmony oscillator and actually test them, okay, using experimental results. Okay. So I think that's probably it for the case of, yeah. Oh, there is another thing. So this from the vibrational thing. Now, there was another table before which actually looks at the rotational thing. Okay, so let's cut and paste that again. Unfortunately, it's not the same, apart from it's not altogether the same diatomic molecule, but you can actually look at the case of the uh, uh, hydrogen molecule here, okay, and also the hydrogen chloride. Okay, and you can see the magnitude for the case of the uh, vibrational states are much higher. Okay, this is higher frequency here compared to the rotational case. Well, it's actually, your B is a different thing, but one could actually, okay, if you want to look at much more properly, is this temperature thing. Again, this is much higher for the case of the rotational energy. So at lower temperatures, in other words, one would see that, okay, your rotational energy states get excited. Rotational states get excited, but not the vibrational states. Okay, because your vibrational states require a higher temperature. Okay, so in other words, sometimes in the book it calls your vibrational states gets frozen. You don't see that. Okay, so I think that's sort of completes the vibrational case. So the other thing is to look at some other topic, which is on the partition function, and the other thing is equipartition theorem. Perhaps we can take a break at the moment, say for 5 minutes. Is that okay? So we'll come back in 5 minutes. So are we all back? Should we start? Okay. So the next thing to do is to look at sort of generalizing what we have had so far. So this is about factorizing partition function. Now, what we have so far is we treat previous treat each motion separately, but you know that as a physical entity, for example, the diatomic molecule will have all possible motions. So we need a way to add up all the energies in some sense, okay? So in other words, what we're going to do is to assume a certain feature that with all these possible motions, one should have some kind of total energy. So, and the assumption here, the total energy is just simply a sum of some terms, like what's written in the book, that depends on, and each term depends on a particular quantum number. Okay. So addition of terms, and each term depends on one quantum number. So let's make this specific by concentrating on your diatomic molecules specifically. So we had what? We had the vibration motion previously, which is approximated by your harmonic oscillator. So we can think of the first term is just given by these energy levels of the harmonic oscillator, n plus a half. And then what you have, where's the cursor? The next thing, the previous thing that we did before vibration is rotational motion. And your rotational motion is given by another function which depends on this angular quantum number, which is given by h bar squared L plus 1 divided by 2I. Okay, and then finally we have the one before that, we have the translational motion. So I can write this as, maybe just as epsilon I with h bar squared pi squared on 2ml squared. This is particle in a box. And then you have your three different quantum numbers added up, well, the square of them added up together, and we can write this as Hn1 plus Hn2 plus Hn3. So in the end, what we have is just like the one on top. We're going to add all these terms together. So the total energy, which I write as capital EI, is given by H bar squared pi squared on 2 ml squared n1 squared plus n2 squared plus n3 squared plus H bar omega n plus a half plus H bar squared L plus 1 on 2i. Now, this is really an assumption. So what is the assumption? The sum assumes independence of H motion. But is it really so? Not quite, really, because your vibration reality, your vibrations affect the rotations. Why? Remember, the rotations depend on this mass, what do you call this? Moment of inertia, sorry. And then, as you have this vibration, for example, you can have this kind of mode of vibration, then your I changes, for example. Okay? Or you have this other mode over here, then your I again changes. Okay? So in other words, really the vibrational states will somehow have an effect on the rotational states. But the shift of energy, okay, the energy shift are quite small. Quite small, and we can sort of ignore it. Okay. So, okay. Now one could try to put all these energy levels together and write a partition function. Okay. And the way we write it, so let me so I'm going to have to push this again because my tab is quite small, so I need some writing space. So partition function can now be written as follows. Your Z is going to be the sum of all these quantum numbers. This for the translational, then you have your vibrational, then you have your what you call rotational. Okay, and then remember, if you have energy degeneracies, which in the case of the rotational, you have your rotational degeneracy here, multiplied by the exponential EI, which is now the total energy, divided by kBT. But what happens, okay, remember that your EI will have the three sums. Okay, so your EI, the one previously, let's just label this as, maybe I write down here, EI is translational plus E vibrational plus E rotational. Okay. So when you put this into this AI, so you just simply have this exponential with the sum there, but each of these sum can be separated out, and then you have your exponential multiplied to each other. So in other words, one could actually do the factorization here. Factorize due to sum in exponent. We have the following. Z is now composed between the partition function for your translational, partition function for your vibrational, and the partition function for your rotational. And this is a common feature that exists when you have sort of contribution of your states corresponding to whatever motion is supposed to exhibit, or whatever states that's involved. If they are independent of each other, then essentially you're going to get your partition function as a product. Okay, so that's the main gist of the thing. So one could, for example, an example here, for example, would be the spin states. Okay, spin states will contribute another factor of partition function to this total partition function. But sometimes what happens, this contribution are going to be ignored. Okay, so may contribute to partition function, but what happens is that if the energy of the spin state is large, okay, if energy here is spin, for example, larger than the what you call the energy of the thermal energy at the what you call the temperature T, then one could really ignore this. Just like the ones that we shown before, where your vibrational states gets frozen in a way because at lower energies there's not enough energy to excite the vibrational states. Okay, similarly the same thing happens over here. Okay, so okay, what else do I want? Okay, well, once you have this product of your partition function, then you can almost immediately see for free energy, which is just like your energies before, because of the log of your partition function, then this will up into addition again. So we can have d log of z translational, okay, plus log of z vibrational, and then log of z of rotational. Okay, so again it becomes a sum. See, and you know that most of the other quantities that you're going to calculate is going to be coming from the free energy. So particularly one can see how this affects say the heat capacity, for example. So whether you have all the contributions going to be coming in or not. So here I'm going to have to cut and paste another picture from the book. So here is the two cases of two different molecules. Here is a molecular hydrogen thing. Where are we? Oops. Getting confused about. Never mind. Okay. So I'm going to cut and paste that here and enlarge this a little bit. Okay, so let me just actually the explanation is in the book. So what happens at low temperatures, you have that sort of going to decay kind of thing. So and then as you so essentially your CV decreases exponentially at low temperatures. So that corresponds to this part. Okay. But then it peaks somewhere as T increase, CV peaks. There's a value here. Is at 21K. This is where from liquid hydrogen, then it boils to the molecular hydrogen gas, and then that thing drops to, what was it, 20 joule per mole per Kelvin, which is around here. And this is roughly phi r over 2. Now, the numbers phi over 2 will make sense when we talk about equipartition theorem later on. Okay. So, should have the picture in the view. What else? Yeah, above 100K, there you start to see your rotational states get excited. And your, oh, actually this is CP. Yeah, sorry, this is CP. So CP, well, CP and CV is going to be related by something like that. I can't remember precisely the number here. I think it's just that. So CP gets rise up to 7R02. So again, this number 5 and 7, where does it come from? Well, later on we talk about equipartition theorem and the degrees of freedom. Then you can understand why this actually happens. Okay. Then at this stage, your vibrational states are not yet excited, but above 1000K, then the vibrational states start to get excited. not sure whether it's in the picture or not, but yeah, so you can see the increase over here. Okay, so in other words, how this actually comes about, you can see it comes, well, from your free energy. One can talk about, one can derive your entropy, okay, and then from your entropy, one can derive your heat capacity. But one has to remember what is the temperature here. So if the temperature is high enough to excite everything, then all contribution is there. If it's not, then not all the contribution will be dominating, but no, maybe only the translational dominates, or the rotational dominates. Okay, so this is the kind of picture that we have. The other example that was given was the carbon monoxide thing. So let me just describe that for completeness. So in the case of the carbon monoxide, it seems to be less prominent in terms of the increase and decrease. So this is for carbon monoxide. So here the changes are less pronounced. Okay, but you can see as you go beyond, say, 1,000 here somewhere, okay, T goes more than 1,000, then you can see they start to increase, because there you start to see your vibrational energy starts to come in. Okay. So all the things that we have done so far is to be able to have a complete picture of this, contributions to the heat capacity. Okay, so let's try to move on. Some of the sections in the book, I don't think I want to go through too much, so I will just go through one section on the equipartition function, equipartition theorem, and then the rest you can either wait for my notes or just read from the book. Okay, so let me go through equipartition theorem. Sorry, maybe I should just clear the whiteboard. So here is, oops, I don't want red. So we'll be looking at equipartition theorem, which relates to the contribution of each degree of freedom towards the, say, heat capacity. Okay, but we are going to do this for the case of the classical gas. Now, really, how should I say, the classical case is a bit more complicated. So that's why in this particular book of Bowley and Sanchez, the classical case comes later, but historically this comes earlier. So Boltzmann and what's the other person? Boltzmann and Gibbs. Okay. was already able to write down expression for entropy. Okay, so there must be a way of trying to describe how. Remember, entropy is coming from your different configurations of the states. See whatever states that's going to be. So we're going to describe this a little bit. Okay. The problem with the classical gas is the fact that the states are described by the variables of what we call the phase space, Q and P. Okay, so Q is what? Q is your position in general coordinates. Okay. Have you done, by the way, have you done classical mechanics? Maybe I should see you. Can somebody say yes or no?
Semester.
Oh, this Sam. Have you gone into Lagrangian mechanics yet? Not yet. Okay. But the idea is the classical state is given by this pair of variables. Okay, one of them is the position. The other one could be your momentum. Okay, if later on, okay, this is your. Okay, maybe I should say this because you're going to learn it anyway, right? This is what we call the classical mechanical state in Hamiltonian mechanics. So you use the pair of position and momentum. Equivalently, one could use this. You have seen this notation before? Q dot. Speak out because I can't see you when I'm. Pardon? Yes, it's the velocity. Okay, this is the time derivative of your position. So this is the classical mechanical state in Lagrangian mechanics. So really your Hamiltonian mechanics and Lagrangian mechanics are just a mathematical framework to describe classical mechanics. Newtonian mechanics, for example, is going to be, so let me just explain that. Newtonian mechanics are the one that you learn from school days until university, okay? Essentially, the framework is not really well defined because it's actually a framework that is based on experiments. It's phenomenological. The case of the Hamiltonian mechanics and the Lagrangian mechanics, it comes about through a very important principle called action principle, which is something that you should learn in vibrational calculus. So it has this particular mathematical framework that actually no, it's equivalent to the Newtonian mechanics in the end. Okay, so that's the main thing. But the idea of that is that you have this pair of variables that gives you the state of the mechanical system. Okay, so let me push this thing out. So what's the problem with this? The problem with this is the fact that your Q's and P's are continuous variables. Okay, so in other words, if one needs to define the state using a continuous variable, it's going to be really difficult because of there are infinite points that you want to look at. So that was the complication, is essentially. That's why when I first taught statistical mechanics, I used a different book, and it started off with the classical case, and that is a bit unfriendly to students. So you're lucky to have this different book for this time. Okay, so let me just mention what's the problems again. What one needs is essentially you have your phase space. In order to describe your configurations, one needs to break it down into grids. That way, so here again, I'm simplifying things because I can only draw a single axis over here. So here's your Q and here's your P. But really in the 3D case, then you will have what? Your each of this grid, so to speak, is really a box. Okay. So you have, say, for example, for the case of a position, then this would be Q. Maybe I should write the differential first. So this would be dqx, dqy, and then this is dqz. So you have all these little cubes. Okay, sort of discretization of your position. And similarly for the case of the momenta. Okay, sorry for the horrible diagram, but again you have the same picture here: dpx, dpy, dpz. Okay, and one could make this discretization, if you like, as small as possible. And if you make it smaller, means better precision. That means you can actually point out anywhere on the space, then you can get the small cube around that point. Okay, but this would actually cause a problem. Okay, because once you have too many grids, then you have problem in dealing with infinite number of grids. Grid boxes. And when one does that, remember the infinite number of grid boxes would tell you about the number of configurations. So there will be an infinite number of configurations. And Boltzmann's formula for your entropy is what? KB log W. So if you have infinite number of configurations and you have infinite entropy, which you would not want to have that. So in other words, somehow Boltzmann made some kind of approximation so that this thing is still considered as finite. Okay. So how does this connect with the case of the previous discussion? Well, okay, perhaps I should also say that in the quantum case, there's no problem. Why? Because there's an uncertainty principle. There you cannot remember what is uncertainty principle. Delta Q, delta P must be always bigger than h bar over 2. So you cannot make together, okay, you cannot make the grid of your phase space. So this is essentially a limit of how small the volume of the phase space should be. Not very, my writing doesn't match with what I'm saying. Control Z, how small the volume of the phase space. Okay. So in a way, in this way, that's why the quantum case is simpler, and also the fact that in the quantum case, you talk about discrete energies. Okay, so that's why when we started off with all this simple quantum case, because it's easy for us to write down the partition function. Okay, so in the case of this classical case, how does the partition function looks like? Okay, so let me try to do this in a simple way, I suppose. Your partition function should really comes from the grid boxes that you're supposed to have. Okay, so there will be Z given by the following. So remember, you need to integrate over all possible variables. So that's why you have this infinite point, but you have this Boltzmann factor here. Yes. Okay, this is the case of 1D first. On KBT. So this is the case of one-dimensional where you have, oops, my whiteboard seems to froze. Are you still hearing me and seeing me? So I'm not sure what happened just now. You seeing the whiteboard? Okay, great. So I can still continue. Let me just try to finish this and then we'll stop. So that is the one-dimensional partition function. You can generalize this. Again, one could actually write this as Zx. Then you can start to write for your, because of the exponential thing. So you have this factorization again. Okay. But the thing is, over here you have this infinite integral that one needs to worry about. So one needs to have a special form of your energy here. So the special form that one usually assumes, where is my cursor? One needs to your harmonic oscillator energy kind of thing. So it has the sum of the two squares thing. Okay, so this will represent your kinetic energy, this will represent your potential energy. Then one could write this as follows. If you have this kind of energy inside this integral, then you can actually integrate. Okay, so let me just write that down. Z equals to 1 over h. Oh, I've forgotten that your h is the size of the box or the size of the grid. Q dp E minus alpha q squared minus beta p squared, the whole thing on kbt here. So one can use this formula that one knows. You take the integral of e minus m squared h squared from minus infinity to infinity. This is the Gaussian function, Gaussian integral. This is root pi over m. Okay, so one can use this to evaluate this. So there you'll find that your partition function is given as a finite number t over h alpha by kbt over h beta. Okay, please work that thing out. And one can write down your, say, free energy, which is, you know, that is equals to T log Z, and then calculate your entropy and then your CV. Then you'll find that your, for this particular case, your heat capacity just gives you the Boltzmann constant. Now, this is not quite realistic because you're assuming a kind of a harmonic oscillator thing. So for the case of a free particle, for example, you don't have this quantity. So what does one do in that particular case? So your alpha, so free particle, alpha equals 0. Then one cannot use the Gaussian formula to integrate your dq. So really, in this particular case, one needs your q integral to be over a finite range. So in that particular case, you can modify that partition function earlier into the following. Z equals to 1 over h. So the integral is going to be finite here. And this will be just your p squared here. And this you can evaluate to be delta q on h. And then you have that same square root thing given by that. Again, calculate your f. From your f, calculate your heat capacity. Why is it not appearing? So maybe I'll push this thing up. Then over here, instead of getting kb, you have half kb. So you can have a feeling over here what happens there if you have both P and Q, both P and Q having that quadratic feature there, it will contribute to the heat capacity with half kb. So you have two of them, say alpha q squared, then you have half kb plus half kb, and that gives you the earlier result of kb here. Okay, so this is essentially the context of the equipartition theorem. Which says that every degree of freedom, in this case including the Q and P, contributes a factor of average. Okay, remember that the degree of freedom must exist in terms of a quadratic, quadratic form. Okay, contributes an average energy of half kBT and contributes to the heat capacity as half kb. So if you have both P and Q, then you have half kBT plus half kBT, and then for heat capacity half kb plus half kb. And this idea of this degree of freedom, sort of the quadratic form, contributes that works in general. So you can read in the book of the read the rest of the section of the book to see how this works. So there you can start seeing that, okay, why do you have your 502 previously? Okay, and then you have 702, and then you can see that everything in terms of this odd powers over 2, sort of odd multiples over 2 kb thing. Okay, so you can read the rest of the section, and I think I want to stop at that point. Okay, the rest of the chapter I will try just to type up the notes, and then let me just check. So far we have covered chapter 4. Well, before that was chapter 3, which is on probability and statistics, which is not really the main part of the course, because that's just a tool. Chapter 4 and chapter 5 will be the material for test 2. Okay, so there will be an assignment hopefully either today or tomorrow. Okay, and then I leave it up to you whether you want your test next week or the week after next. Because I've lost count. Essentially, I've lost count. What week is this? Because of the break that we had before, and we still need to replace, I think, at least 1 or 2 lectures. Okay. Why? Okay, then we have not next week, then the week after next. Okay, so that gives you a bit of time to look at the assignment. Hopefully, I'll post it up in within this week. Okay. Okay, that's all for today. So let me take your attendance first. Okay, so I think that's it. So thank you everyone. So hopefully see you next week. Okay, thank you.